Close your eyes. Let everything go still. Your body is heavy now. Your hands are open. Your shoulders have dropped away from your ears, just slightly, the way they always do when the day finally releases you. Breathe in slowly. And breathe out. Good. Tonight, I want to take you somewhere ancient, somewhere so old that the word old stops meaning anything, somewhere that existed long before the Earth, long before our sun, long before the first complex molecules ever tangled themselves together in the shallow waters of a young and restless planet and began slowly, improbably, magnificently to become alive. Tonight you are going to witness the life of a star. Not one star, many stars. You are going to travel through time itself, through billions of years of cosmic history, and watch as the universe learned, slowly and through great patience, how to make light, how to make warmth, how to make the very atoms that now sit inside your chest, rising and falling with every breath you take. But first, before any of that, there was darkness. Not the darkness of this room, not the darkness of a night with the curtains drawn, a deeper darkness than anything you have ever experienced, the darkness of a universe that had just been born and had not yet learned how to shine. In the beginning, the universe was hot and dense and bright. But as it expanded, as it cooled, as the first simple atoms formed and the energy spread thin across the growing void, the light faded. The universe entered what astronomers call the cosmic dark ages, a period of hundreds of millions of years when there were no stars, no galaxies, no light of any kind. Just hydrogen. Just vast, cold, slowly drifting clouds of the simplest element in existence. Hydrogen atoms adrift in the dark, quiet, patient, waiting for something to begin. Imagine that darkness now. Not with fear, with wonder, the way you might stand outside on a very still night and feel the size of things. The universe, for hundreds of millions of years, was simply waiting, gathering itself, letting gravity do its slow and patient work. And gravity, as it always does, was pulling things together. Here and there across the dark, hydrogen clouds began to clump, slowly at first, then faster, gravity drawing atom to atom, molecule to molecule, the cloud growing denser at its center, warmer, the atoms moving faster and faster as they were compressed together by the weight of everything above them. The dark was about to end. Something was about to be born. Let your body sink deeper into where you are lying now. Feel the weight of your arms, the heaviness of your legs. Let gravity do for you what it has been doing for the universe since the very beginning, drawing things together, bringing things to rest, pulling you gently, patiently, inevitably toward stillness. You are in good hands tonight. The oldest hands in the universe. The hydrogen cloud is collapsing now. In your mind, watch it. Hundreds of light years across, this vast dark cloud is slowly, over millions of years, pulling inward, the center growing hotter, 100 degrees, 1,000, 1,000,000, the pressure building to something almost unimaginable, atoms being crushed together so hard, so hot, so relentlessly, that they begin to do something that has never happened before in this corner of the universe. They begin to fuse. Hydrogen atoms, under this impossible pressure, are pressing together so hard that they merge, two hydrogen nuclei becoming one helium nucleus, and in that merging, in that moment of fusion, a tiny amount of matter is converted directly into energy, into light, into heat. And for the first time in hundreds of millions of years, the dark has a light in it. A star is born. Part 2. The Nursery of Stars. The place where stars are born has a name. A nebula. From the Latin word for cloud, and clouds they are, but not the soft white clouds of an Earth afternoon. These are clouds that span hundreds of light years. Clouds made of hydrogen and helium and dust, glowing with the light of the young stars already ignited within them, lit from inside the way a lamp glows through a paper shade. The most famous of these stellar nurseries is one you may have seen in photographs without knowing its name. The Eagle Nebula, 7,000 light years from where you are lying right now. At its heart, 3 vast towers of gas and dust rise like cathedral columns into the surrounding cloud, each one several light years tall, each one tipped with the dense knots of collapsing gas that will, over the next few million years, become new stars. Astronomers named these towers the pillars of creation. And creation is exactly what they are. Let yourself drift there now. Imagine floating in the warm glow of a nebula. The light here is not white. It is tinted red and gold and deep rose, the hydrogen gas glowing in the ultraviolet light of the young hot stars nearby. The dust catches the light and scatters it, so everything has a softness, a diffusion, like a room lit by many candles rather than a single bright source. It is warm here. Not in any physical sense you would feel on your skin, but visually, emotionally, there is a warmth to this light that the cold dark of open space does not have. This is a place of making, of beginning, of the universe doing what it does best when given enough time and enough matter and enough patience. Creating. Stars are not born alone. When a large cloud collapses, it rarely forms just one star. It fragments. Different regions of the cloud collapse at slightly different times, and dozens or hundreds of stars ignite within the same nebula over the course of millions of years. A family of stars, born from the same cloud of gas, orbiting together through the galaxy for billions of years before the gentle gravitational tugs of passing clouds slowly pull them apart. Our own sun was born this way. 4.6 billion years ago, a cloud of gas and dust in what would become the Milky Way began to collapse, perhaps triggered by the shock wave of a nearby supernova, perhaps simply by its own patient accumulation of mass over millions of years. The cloud fragmented, and dozens of stars were born. Our sun was one of them. Somewhere out there, spread across thousands of light years of the galaxy, are the sun's siblings, stars born from the same cloud of gas, made of the same material, the same age, now far apart, drifting through different regions of the galaxy, probably with their own planets, their own systems, their own stories. The universe is full of families separated by distance and time, but made of the same stuff. Always, fundamentally, made of the same stuff. Breathe in slowly. Breathe out. When a star first ignites, it is not yet settled. It is a protostar, unstable, variable, still gathering mass from the cloud around it, still contracting, still finding its balance between the inward pull of gravity and the outward pressure of the nuclear fire at its core. Young stars are restless. They flare, they pulse, they shoot jets of superheated gas out from their poles, carving glowing tunnels through the surrounding nebula. They are bright and variable and unpredictable, the way all young things are, full of energy, full of change, not yet settled into the long steady burning that will define most of their lives. But eventually, after tens of millions of years, they find their balance. The contraction stops. The nuclear burning steadies. The star reaches what astronomers call the main sequence, the long stable middle age of a star's life, where it will spend most of its existence, shining steadily, burning hydrogen into helium day after day, year after year, millennium after millennium. Reliable, patient, warm. Like a lamp left burning in a window. Let your breathing slow now. In and out. The star has found its rhythm, and so are you finding yours, the long, slow breathing of deep rest, the body settling into its own kind of main sequence, its own steady state, the heart beating its patient beat, the lungs rising and falling, everything working exactly as it should, without effort, without thought, just the quiet, reliable machinery of a body that knows how to rest. Part 3. The long burning a star on the main sequence is a study in balance. At its core, hydrogen is being fused into helium. Every second, our sun converts 600 million tons of hydrogen into helium. Every second. Without pause, without rest. For billions of years. And yet the sun is so vast, contains so much hydrogen, that this rate of burning is perfectly sustainable. Our sun has been burning for 4.6 billion years. It has enough hydrogen left to burn for another 5 billion years. 10 billion years of steady burning, of reliable light, of patient warmth. 10 billion years. Let that number drift through you without trying to hold it. Some things are not meant to be understood intellectually. They are meant to be felt. The way you feel the age of a very old tree when you press your hand against its bark. The way you feel the depth of the ocean when you stand at the shore and look out at the horizon. 10 billion years of light. 10 billion years of warmth, reaching out across space to wherever warmth is needed. Different stars burn differently. The most massive stars, 10 or 20 or even 100 times the mass of our sun, burn so hot and so fast that they exhaust their hydrogen in just a few million years. Brilliant and profligate, they blaze through their fuel like a fire that burns too bright. Their lives are short by cosmic standards, spectacular, intense, and brief. The smallest stars, the red dwarfs, burn so slowly and so coolly that they will last for trillions of years, far longer than the current age of the universe. They are the tortoises of the stellar world, dim and unhurried, red and patient. They will still be burning long after every other type of star has burned out and gone dark. Our sun is somewhere in between. A medium star, a yellow dwarf, not the brightest, not the dimmest, not the most spectacular, not the most humble, just right perhaps for the kind of steady, reliable warmth that life requires to get started and keep going. Inside a star, the process of fusion is extraordinary. At the core of our sun, the temperature is 15 million degrees. The pressure is 250 billion times the atmospheric pressure at Earth's surface. Under these conditions, hydrogen nuclei, which normally repel each other, are forced close enough together that the strong nuclear force, the strongest force in nature, can grab them and fuse them together. The energy released in this process travels outward from the core, but not quickly. A photon of light created at the core of the sun takes, on average, 100,000 years to reach the surface. 100,000 years of bouncing, absorbing, and re-emitting, working its way outward through the dense plasma of the stellar interior. 100,000 years just to escape. And then, once it reaches the surface, it travels the 93 million miles to Earth in just 8 minutes. The light that warmed your face today began its journey 100,000 years ago, when our ancestors were painting on cave walls, when the Ice Age was at its height, when everything that would eventually become your world was still unimaginably far in the future. That light traveled all that way. For you. Let your eyes stay closed. Let your thoughts slow like photons moving through dense plasma, taking their time, in no hurry, moving toward the surface gently, slowly, across vast distances of time. You have all the time you need tonight. There's nowhere to be. Nothing to do. Just the long, slow drift toward rest. The surface of a star is not solid. It is a roiling, churning sea of plasma. Enormous convection cells rise and fall, each one the size of a continent, carrying heat from the interior to the surface and back. Magnetic fields loop and twist through the plasma, creating sunspots, cooler, darker regions that appear and disappear over cycles of years. Solar flares erupt, shooting streams of charged particles millions of miles into space. And yet from a distance, from the cool darkness of space, a star looks still. A perfect sphere of steady light. All that turbulence contained within, all that activity hidden by distance. From far enough away, the most violent and energetic object in the solar system looks like nothing more than a warm and steady light in the dark. Things often look quieter from a distance. Your own life, seen from far enough away, from high enough above the details, is probably the same. All the noise and turbulence of the day, the small anxieties, the unresolved questions, the things that felt urgent, from far enough away they are just warmth, just light, just a life burning steadily. Part 4. The Turning Point. Nothing burns forever. Even the most patient star, even the steadiest and most reliable light in the universe, eventually reaches a turning point. The hydrogen at the core runs out. The balance that is held for billions of years begins to shift. For a star like our Sun, this moment comes after about 10 billion years of main sequence burning. The hydrogen at the very center is exhausted. There is no more fuel for the fusion that has been pushing outward against gravity all this time. The core begins to contract, to compress, to heat up further. And something changes. The hydrogen fusion does not stop. It simply moves. As the core contracts and heats, a shell of hydrogen just outside the core reaches the temperature needed for fusion. A shell of burning, surrounding the dead helium core. And this shell burning is more energetic than the core burning that preceded it. The outer layers of the star begin to expand. Slowly at first, then more. The star grows, swells. Its outer surface, moving further from the hot core, cools and reddens. Over hundreds of millions of years, the star transforms from a steady yellow main sequence star into something vast and red and luminous. A red giant. When our Sun becomes a red giant, in about 5 billion years, it will expand to perhaps 100 times its current size. It will swallow Mercury. It will swallow Venus. And the Earth, if it still exists, will either be swallowed too, or will find itself orbiting inside the outer atmosphere of what was once a star the same size as the Sun. The oceans will have boiled away billions of years before that. The atmosphere will be long gone. Whatever life exists on Earth, if any does, will have had to find another home long before the Sun begins its expansion. But this is not a sad story. This is how it is supposed to go. This is the natural life of a star, the arc that was set in motion the moment the first hydrogen atom fell toward the center of a collapsing cloud billions of years ago. Every star that ever burned has been moving toward this moment since the day it was born. The expansion of the outer layers, the reddening, the swelling. Not a catastrophe. A transformation. Breathe in. Breathe out. Inside the red giant, the helium core is still contracting, getting hotter, the temperature at the center climbing toward 100 million degrees. And when it reaches that threshold, something new begins. Helium fusion. 3 helium nuclei under these extreme conditions can fuse together to form a carbon nucleus. This is called the triple alpha process, and it is one of the most important reactions in the universe because carbon is the foundation of chemistry. Carbon is the backbone of every organic molecule. Carbon is, in a very real sense, the element that makes complexity possible. And it is being made right now. Inside aging stars all across the galaxy, helium is being fused into carbon. Carbon is being fused into oxygen. Oxygen into neon. Neon into silicon. Silicon ultimately into iron. The periodic table is being written in stellar cores. The atoms that will one day make up planets and oceans and forests and the bodies of living things are being forged right now in the hearts of dying stars. Dying, in this sense, is not an ending. It is a kind of generosity. Your body contains carbon that was made inside a red giant star billions of years ago. The oxygen you breathe was forged in a stellar core. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, all of it made inside stars that lived and died before our sun was born. You are the product of stellar generosity. Stars spend billions of years building the atoms that make you possible. And then, when their time came, they released those atoms back into space to drift and gather and eventually, improbably, become something that could look up at stars and wonder about them. Let that settle into you now. Like warmth. Like the warmth of starlight that has been traveling toward you for a very long time. Part 5. The Gentle Death. For a star like our sun, the end comes gently. After the red giant phase, after the helium burning and the carbon building, the outer layers of the star become unstable. The star pulses. It expands and contracts over periods of thousands of years, each pulse pushing more of the outer atmosphere into space. Slowly, over tens of thousands of years, the star sheds its outer layers entirely. These layers drift outward into space, a sphere of glowing gas, expanding slowly away from the dying star at the center, lit by the ultraviolet light of the hot exposed core, glowing in intricate patterns, shaped by the magnetic fields and stellar winds of the star that made them. This is called a planetary nebula. Despite the name, it has nothing to do with planets. It was named by early astronomers who saw these glowing spheres through small telescopes and mistook them for the disks of distant planets. In reality, they are far more beautiful and far more significant. They are a star's last breath, its final exhalation. Released back into the galaxy. To become part of something new. Planetary nebulae are among the most beautiful objects in the known universe. The Helix Nebula, 2,500 light-years away, looks like a vast eye staring out of the cosmos. rings of glowing gas in blue and red and gold, surrounding a tiny white point of light at the center. The ring nebula in Lyra, a perfect glowing oval of blue and green. The butterfly nebula, its wings of gas stretching 2 light years across, shaped by the fast stellar winds of the dying star within. Each one different, each one shaped by the particular history of the star that made it, the magnetic fields, the rotation rate, the presence of a companion star nearby. Every planetary nebula is unique, a fingerprint of the star that breathed it out. A last, beautiful individual act. At the center of the planetary nebula, what remains of the star is shrinking. The outer layers are gone. The nuclear burning has stopped. All that remains is the core, a ball of carbon and oxygen, about the size of the Earth, but containing roughly half the mass of the original star. Incredibly dense, incredibly hot, still glowing white, with the residual heat of billions of years of nuclear burning. This is a white dwarf. The final state of a star like our Sun, the endpoint of a 10 billion year journey. A sphere of ultra-dense matter, no longer fusing, no longer burning, just slowly cooling over billions of years, radiating its stored heat into the surrounding darkness, like a coal taken from a fire, glowing orange and then red, and then fading, slowly, over an almost incomprehensible span of time. A white dwarf cools very slowly. A newly formed white dwarf is extraordinarily hot, 100,000 degrees at its surface, but it is no longer producing energy. It is simply releasing what it has stored. And because it is so dense, so tightly packed, the cooling takes an incredibly long time. Astronomers calculate that it would take longer than the current age of the universe for a white dwarf to cool completely, to become a black dwarf, a cold, dark, inert sphere of carbon drifting silently through space. The universe is not yet old enough to have produced a single black dwarf. Every white dwarf that has ever formed is still glowing, still warm, still holding the memory of the fire that made it. There is something deeply comforting about that. The idea that warmth persists, that the heat of a fire once kindled does not simply vanish but lingers, slowly fading over billions and billions of years. That the light of a star, even after the star itself is gone, continues to glow in the darkness. Nothing is simply lost. Everything transforms. The energy that burned in the core of a star for 10 billion years becomes the gentle glow of a white dwarf. The atoms built in that stellar core become the dust of a planetary nebula. The dust becomes the building blocks of a new solar system. The new solar system grows planets, the planets grow life, and life eventually looks up and wonders about stars. The universe is very good at recycling and very patient. Let your body be still now. Let your breathing be slow and even and deep. You are in the later hours of the night, when the body's own temperature drops slightly, when the heartbeat slows, when the muscles release their last tensions, and the mind begins to drift away from the shores of waking. This is your body's own version of the long, slow cooling, the patient, restful release of the day's energy. Not a loss, a transformation, the busy heat of the waking mind becoming the deep, cool stillness of sleep. Part 6. The Violent Death. Not all stars die gently. For the most massive stars, the stars that burn 10 or 20 or 50 times hotter than our Sun, the end is not a slow exhalation, not a gradual shedding of outer layers, not a gentle drift into white dwarf retirement. For the most massive stars, the end is an explosion. one of the most energetic events in the known universe? A supernova. Here is what happens. A massive star burns through its hydrogen quickly, then its helium, then its carbon, then its oxygen, then its silicon. Each stage of burning lasts a shorter time than the one before, because each successive fuel releases less energy per reaction. Hydrogen burning lasts millions of years, helium burning hundreds of thousands, carbon burning a few thousand years, oxygen burning a few months, silicon burning just a few days. And then the silicon is gone. What remains in the core is iron. And iron is different from everything that came before. Every element up to iron releases energy when fused. But iron absorbs energy rather than releasing it. You cannot burn iron. You cannot extract energy from iron fusion. Iron is the end of the nuclear road. The core, now made of iron, can no longer support itself against gravity. In less than a second, the iron core collapses. What happens in that fraction of a second is almost beyond description. The core, which was roughly the size of the Earth, collapses to a sphere about 20 kilometers across. In less than a second, the density becomes so extreme that electrons and protons are crushed together into neutrons. The core becomes, in that instant, essentially a giant atomic nucleus, a neutron star. The collapse releases an enormous amount of energy, more energy in that fraction of a second than our sun will release in its entire 10 billion year lifetime. Most of this energy is carried away by neutrinos, ghostly, nearly massless particles that interact with almost nothing, passing through the star as if it were not there, carrying their energy out into space. But a tiny fraction of this energy, just 1%, goes into the outer layers of the star. And 1% of something that large is still incomprehensibly powerful. The outer layers are blasted outward at a significant fraction of the speed of light. The star explodes. A supernova, at its peak, can outshine an entire galaxy. 200 billion stars, each one a sun, each one shining with its own light, and a single supernova can briefly outshine all of them put together. In the year 1054, Chinese astronomers recorded a new star appearing in the sky, so bright it could be seen in full daylight for 3 weeks. So bright it cast shadows at night. They called it a guest star. It remained visible to the naked eye for almost 2 years before fading. What they were seeing was a supernova, the death of a massive star 8,000 light years away. The explosion had actually happened 8,000 years earlier, when the light began its journey toward Earth. It arrived in 1054 and was bright enough to be seen in the middle of the day. Where that star died, there is now a nebula. The Crab Nebula. A tangled web of glowing filaments, 10 light years across and still expanding, still carrying outward the violence of that long-ago explosion. At its center, spinning 30 times per second, is the neutron star that was born in the collapse, a city-sized ball of matter so dense that a teaspoon of it would weigh 1 billion tons. Death, in this case, made something extraordinary. But here is what I want you to hold on to as your eyes grow heavy. The supernova is not just an explosion. It is a distribution. All those heavy elements built up in the stellar core over millions of years of burning, the carbon, the oxygen, the silicon, the iron, and in the supernova explosion itself, elements even heavier than iron, elements that can only be made in the extraordinary conditions of a stellar explosion: gold, silver, uranium, platinum. All of it blasted outward into space. seeding the surrounding gas clouds with complexity, with the building blocks of planets, with the raw materials of chemistry, with the atoms that will eventually, given enough time and the right conditions, become the ingredients of life. The gold in a wedding ring was made in a supernova. The uranium that powers nuclear plants was made in a supernova. The iodine in your thyroid gland was made in a supernova. Every violent death a generous gift. Every explosion a seeding. Every ending a beginning. Part 7. The neutron star. After the supernova, in the place where the iron core collapsed, something remains. A neutron star. The most extreme object in the universe, short of a black hole. A neutron star is roughly 20 kilometers across, about the size of a city, and yet it contains 1.5 times the mass of our sun. All of that mass compressed into a sphere you could drive across in 20 minutes. The density is almost incomprehensible. A single teaspoon of neutron star material weighs approximately 10 million tons. The gravity at the surface is 200 billion times stronger than the gravity at Earth's surface. The magnetic field is 1 trillion times stronger than Earth's. And it spins. When the core collapses, just as a spinning figure skater pulls in their arms to spin faster, the collapsing core spins faster and faster as it shrinks. A star that rotated once every few weeks becomes, in the collapse, a neutron star that can rotate hundreds of times per second. Hundreds of times per second. These rapidly spinning neutron stars, beaming radio waves from their magnetic poles, are called pulsars. They sweep their beams of radio waves across the sky like cosmic lighthouses. So regular, so precise, so unvarying in their timing, that when the first one was discovered in 1967, astronomers briefly considered whether it might be a signal from an alien civilization. They called it, half-jokingly, LGM1, Little Green Men. It was not aliens. It was something more wonderful than aliens. Oh, it was the universe's own clock, a spinning ball of neutrons left over from a stellar explosion, keeping time with a precision that rivals the best atomic clocks ever built. Neutron stars sometimes have companions. Many stars form in pairs, binary systems, 2 stars orbiting each other, born from the same cloud of gas. When the more massive star dies in a supernova and becomes a neutron star, it sometimes survives with its companion still orbiting nearby. And then something remarkable can happen. The neutron star, with its extraordinary gravity, can begin to pull material from its companion. Gas streams across from the companion star and falls onto the neutron star. This gas accumulates on the surface, getting hotter and denser until it reaches the conditions needed for nuclear fusion. And then it explodes, not a full supernova, a smaller explosion, an X-ray burst, a brief violent flash of nuclear fire on the surface of the neutron star. These explosions can repeat, over and over, every few hours or every few days, a neutron star repeatedly igniting the material that falls onto it and blasting it back into space. The universe finds the most extraordinary ways to make fire. Let your thoughts drift now like gas streaming between stars. Not going anywhere in particular, just moving, following the gentle pull of gravity, of rest, of the deep quiet that is drawing you slowly inward. Your breathing is slow. Your body is heavy and still. The neutron star spins in the dark, hundreds of times per second, keeping its perfect time. And you are here, unhurried, unscheduled, with nowhere to be and nothing to count. Let the spinning be for the stars. Let the stillness be for you. There is one more thing that neutron stars can do. Sometimes two neutron stars orbit each other, two dead stellar cores, each city-sized, each containing more than a solar mass of matter, spiraling around each other in a deadly gravitational waltz. Over millions of years, they lose energy by emitting gravitational waves, ripples in the fabric of spacetime itself, and slowly spiral inward until they collide. The collision of two neutron stars is called a kilonova, and it is in these collisions, more than anywhere else, that the heaviest elements in the universe are made: gold, platinum, iridium, osmium, all forged in the extraordinary crucible of two colliding stellar corpses. In 2017, for the first time, astronomers detected both the gravitational waves and the light from a kilonova. They watched in real time as two neutron stars merged 1,700 light-years away. They watched the gold being made. They watched the universe doing what it always does, making something precious from something violent, making something new from something ending. Part 8. The space between stars. Most of the universe is not stars. Most of the universe is the space between them. This space is not empty. It is filled with what astronomers call the interstellar medium, a thin, cold, dark mixture of gas and dust, mostly hydrogen, some helium, traces of heavier elements, the gifts of dead stars, dust grains of carbon and silicates, each one smaller than a bacterium, drifting through the dark in clouds and wisps and vast, diffuse hazes. This is where the story begins again. The gas expelled by a dying star drifts outward. It joins the interstellar medium. It mixes with the gas already there. It enriches it. Over millions of years, this enriched gas gathers, condenses, collapses. New stars form. New planetary systems coalesce from the dust. New planets, enriched with the heavy elements of previous generations of stars, provide new opportunities for chemistry, for complexity, for life. The interstellar medium has its own beauty. Dark nebulae, clouds of dust so thick they block the light of the stars behind them, appear as dark patches against the bright background of the Milky Way. The Horsehead Nebula, a dark column of gas shaped from our perspective, like the head and neck of a chess piece, silhouetted against a glowing curtain of hydrogen. Reflection nebulae, clouds of dust lit not by their own emission, but by the reflected light of nearby stars. Blue, because dust scatters blue light more efficiently than red, the same reason Earth's sky is blue. Emission nebulae, clouds of hydrogen energized by the ultraviolet light of hot young stars, glowing red and pink with the light of ionized hydrogen. And dark molecular clouds, the coldest and densest regions of the interstellar medium, where hydrogen molecules form, where complex organic chemistry begins, where the seeds of the next generation of stars are slowly, patiently gathering. On a very dark night, far from city lights, you can see the interstellar medium with your naked eye. Not directly, not the gas itself, but the effect of the dust, the dark patches in the Milky Way, the places where the band of light seems to split or thin or disappear, those are dark nebulae, clouds of dust blocking the light of the stars behind them. Indigenous Australians, who have perhaps the oldest continuous astronomical tradition on Earth, have a different way of seeing the Milky Way. Instead of mapping the stars, they map the dark patches, the dark constellations, an emu, a possum, a snake, all traced in the dusty darkness between the stars. They were mapping the interstellar medium thousands of years before modern astronomy had a name for it. Seeing the dark as something, not the absence of light, but the presence of matter. Not emptiness, but substance. The space between stars is where you are right now, in a sense. Between thoughts, between the busy brightness of the day and the deep rest of sleep, in the interstellar medium of consciousness, where things are quiet and dark and cold, but not empty, where the material of the next day's thoughts is drifting, unseen, slowly gathering into something. You don't need to know what it will become. That is not your work right now. Right now, the drift is enough. Breathe in. Breathe out.